Welcome to the deep dive. Today we're tackling, well, maybe the strangest idea in all of physics, quantum entanglement.
It certainly challenges our everyday intuition.
Absolutely. So our goal here is to really dig into the source material, pull out the key ideas, the concepts, and maybe touch on some of the math behind why it forces such a radical break from classical thinking.
Right. And at its core, entanglement means you have, say, two or more particles whose fates are linked. Their quantum state can only be described as a whole.
Not individually.
Not individually, even if you separate them by huge distances. Miles, light years, it doesn't matter.
And that distance part, that's what leads to the classic, the classic example, right? The paradox.
Exactly. The thought experiment. Imagine a particle decays into two smaller ones flying apart. They are entangled.
Okay.
If you measure the spin of one particle along some axis, let's say you find its spin up.
And instantly.
Instantly, you know the other one, no matter how far away, must be spin down along that same axis. Perfect anti-correlation.
Which sounds like information traveling faster than light, and that's what bothered Einstein so much.
Precisely. He, Podolsky, and Rosen wrote their famous 1935 paper arguing against this. Einstein famously called it spookhafte Fernwirkung.
Spooky action at a distance.
Yes. They proposed there must be some hidden information, local hidden variables carried by the particles from the start, predetermining the outcomes, like matching gloves put in separate boxes.
So, if you open one box and see a left glove, you instantly know the other is right. But nothing spooky happened. It was set from the beginning. Why didn't that explanation hold up?
Well, that's where John Bell came in, much later. He devised a mathematical test, an inequality.
Bell's inequality.
Right. He showed that if these local hidden variables existed, the correlations you measure between the particles would have a certain statistical limit. There's only so much correlation you can get classically.
And when the experiments were actually done?
They violated that inequality. The correlations were stronger than any local hidden variable theory could possibly allow.
Wow. So the connection is real, it's instantaneous, and it's just quantum mechanics, not hidden instructions.
Exactly. It proves the universe isn't locally real in the way Einstein hoped.
Okay, so accepting it's real. The source material then shifts focus. It talks about entanglement not just as a puzzle, but as a resource.
That's a key insight. We move past the spookiness and see it as something functional, something useful. Like energy enables work, entanglement enables certain quantum tasks.
So it's like a raw material for quantum technologies.
In a way, yes. It's quantifiable. You can measure how much entanglement you have, and you consume it to do things. It's fundamental to quantum communication, quantum computing.
All right, let's try to get a handle on the math just conceptually.
Yeah.
How is this inseparable whole captured mathematically?
Well, the defining mathematical feature is inseparability. An entangled state's wave function simply cannot be factored into separate descriptions for each particle.
It's not just particle A's state times particle B's state.
Correct. It's a combined state. Now, to analyze the parts, we use a tool called the reduced density matrix.
Reduced density matrix. Okay, what does that let us do?
It basically lets you calculate the properties of, say, just particle A, effectively ignoring particle B, even though they're linked.
So you could zoom in on one part of the entangled system.
Exactly. And here's where it gets really, really interesting, especially with entropy.
Entropy, usually a measure of disorder or uncertainty.
Right. Now, if the whole entangled system is in a pure state, meaning we know everything possible about it, its total von Neumann entropy is zero. Perfect order.
Maximum knowledge of the combined system.
Precisely. But now, use that reduced density matrix to look only at particle A. Calculate its entropy. Its entropy is greater than zero. Suddenly, you have uncertainty, disorder about the individual part.
Even though the whole system has zero entropy. How?
Because the information isn't in particle A alone. It's stored non-locally in the correlations between A and B. The whole contains more information than the sum of its parts viewed separately. That positive entropy of the subsystem quantifies the entanglement.
I see. So that entropy difference is the measure of the entanglement resource.
It's a key measure, yes. And this resource is what powers applications like superdense coding.
Where you send 2 bits of classical info using just one quantum bit, one qubit.
If you pre-share an entangled pair, yes. And quantum teleportation, of course.
Which isn't like Star Trek beaming, but transferring a quantum state itself.
By consuming entanglement, You transfer the unknown state from one particle to another distant one, destroying the original state in the process. It confirms entanglement is this fundamental, non-classical link.
It really drives home that quantum mechanics operates under fundamentally different rules than the classical world we perceive directly.
It's the defining feature, arguably.
So, wrapping up, entanglement isn't just spooky, it's a core physical reality, a resource, and mathematically described by this idea of inseparability and entropy.
That's a good summary. It's the heart of the quantum revolution.
And maybe even deeper than that.
Yeah.
You mentioned a final thought connecting it to really big questions.
Well, yes. One of the most profound puzzles in physics is the problem of time in quantum gravity. How does time emerge? Some fascinating, though speculative, theories suggest it might arise from entanglement itself.
Entanglement creates time. How?
The idea is, roughly, that the universe seems to evolve because parts of its systems we observe are entangled with other parts that act as internal clocks. The correlations, the entanglement energy between the system and its clock, might be what we perceive as the flow of time.
So entanglement might not just link particles, but might actually weave the fabric of time itself.
It's a mind-bending possibility, but it shows just how fundamental this spooky action might truly be. Something for you to think about.
Indeed. A perfect place to leave our deep dive for today. Thank you. My pleasure.